So considering the figure, the PV diagram, when the system undergoes a process, so we have this one. We have point 1 here, point 2, point 3, and point 4. So we now consider the first law of thermodynamics for a control mass that undergoes a change of state. So we begin by introducing a property energy, which is given the symbol E. Okay, that undergoes a cycle in which it changes from state 1 to state 2 by process. Okay, so here you have this equation of the inexact differential of Q is equivalent to the cyclic integral, or the inexact differential of W. So therefore, let's write this one. In other form, we have the Q 1 to 2 plus, and this one represents the net heat transfer throughout the cycle. So heat 1 to 2 plus heat 2 to 3 plus heat 3 to 4 plus heat 4 to 1. This is equivalent to work from state 1 to state 2 plus work of 2 to 3 plus work 3 to 4 plus work 4 to 1. Okay, so that one. So I have to draw again the PV diagram. So we have 0.1 here. This is our point 2. This is our path A here. this path B, the path C. Okay. So again, the basic statement of thermodynamics. The first law of thermodynamics is Q is equivalent to the cyclic integral of inexact differential of the wave. Okay. The path, and we have this one. Okay, so from path A to B, we have this integral of 1A to A. This is 2A. This is inexact differential of Q plus the integral of 2B to 1B, and this is equivalent to the integral of 1A to 2A. This is the differential of W plus to 1 2B to 1B. W. And from the cycle A C, we have the cyclic integral. No, this is the integral of 1A to 2A. to A. So we have the this is inexact differential of Q plus the integral of 2C to 1C Q. This is equivalent to integral of 1A to 2A W plus 2C to 1C. So considering we have the cycle A to B and this cycle A C. Okay. So what do we have here? So we by taking the difference of these two equations, so we can have the result here. We have integral of 2b to 1b q minus the integral of 2c to 1c. This is equivalent to the integral of 2b 1b w minus integral of 2c to 1c. Okay. Or we can write this one as, or in other form, we have here the integral of 2b to 1b here. This is exact differential of q minus exact differential of w, and we have the integral of 2c to 1c. We have here the exact differential of q minus this one. Okay, so I'll try to recall that the heat, this heat and work is, this is a path function. As we discussed in our previous discussion, we tackled this one. So here, so you notice this one, we have this quantity q minus w. This is a point function. So this is a point function here. So we know that the point function is what? A point function is, this is a property. That is a property. And as I mentioned earlier, it is denoted as E. This is called an energy. This is a property. Unit is in kilojoule. So we have here the exact differential of Q minus the exact. So W is the difference in energy. Okay, so we have here this one. So dE plus this one. Let me believe. So this is now our first law, and in other form we have here Q1 to 2 is, we have the E2 minus E1 plus work 1 and 2, considering two states. We have the state 1 and state 2. So this is our first law. Okay, this E here, the energy, is a property, and we have to consider the, in our previous discussion, we considered the internal energy and the kinetic energy. Okay, so you have this E. You have this review. We have this kinetic energy equivalent to 1/2 mv squared. Another one is you have the potential energy. So given an elevation, we have the PE is mass times G times Z, where Z is the elevation. And also we have here the U, which is the internal energy, and it is dependent on the thermodynamic properties. Okay, so therefore we can write the first law equation, or the energy, as the sum of U here plus the kinetic energy plus the potential energy. Okay, and the difference here, we have the du plus the d of our kinetic energy plus the difference of our potential energy, considering the two states. the initial and the final state. Okay, so therefore, as we write, going to simplify this one, have this E2 minus E1. This is equivalent to U2 minus U1 plus the KE, or this is 1/2 mass times the velocity, since the mass is constant throughout our process or throughout the cycle. So we have, or given in two states, the mass is equal V2 squared minus V1 squared plus the difference of potential energy, which is mass is also constant and the gravity is also constant. We have the elevation at point 2 minus the elevation at point 1. So this is the difference of the E2, the energy, considering we have two states, state 1, state 2, or the initial and final state. Okay, so we have here this considering a system. We have a system here. We have E2 minus E1, and we have this the negative work. We have this negative Q, and then negative W. We have the work generated by system, and we have this input heat, which is positive. You recall the sign convention we've discussed in our previous discussion. Okay, our previous topic. So therefore, the E2 here, E2, or the DE, this is E2 minus E1. This is U2 U1 U2 minus U1 plus 1/2 M V2 squared minus V1 squared plus the mass times the local gravity G. This is Z2 minus Z1 here. So this one, these two quantities here, is the secondary quantities. So called the secondary quantities. Yeah, that's secondary quantities. So given that our system is not moving, so we have no velocity, so basically obviously we have a zero kinetic energy, and have also to consider the reference point or the elevation, which is not changing. So we can now neglect the secondary quantities, given that the potential and kinetic energy is zero. So therefore, the difference in energy E2 minus E1 is simply this one, U2 minus U1. Okay. So the Q from 1 to 2, this is equivalent to U2 U1 plus work 1 to 2. So this is our simplest equation of our first law of thermodynamics, considering or neglecting the kinetic and potential energies, or as we term as the secondary quantities. Okay,